So we have seen that the fundamental group depends on the base point, but we want to understand in what way it really does. Okay, in some sense it drastically does, but in an important sense not very much. Okay, so first of all, suppose your space X has more than one component. Suppose it has a circle and then maybe a disk here. Remember, the disk has trivial fundamental group and the circle has fundamental group Z. Okay, so then if I took the base point here, okay, or at this point x0, the result is very, very different, because any loop here sits in this component, any loop here sits in this component. Okay, so let's just first record clear and but easy observation. So suppose we have x hat contained in x0, not x0, x is the path component containing a base point, okay, containing, let's say, x0 in x. Okay, then it's quite easy to see that pi1, in fact omega of x0 is just omega of x hat x0. Okay, one way, of course, anything here includes here, but any path at x0, all the points are contained in this path components. Therefore, we have the following proposition, which is that pi1 of x0 is just the same, is isomorphic to pi1 of x hat x0. So if we have more than one path component, then the fundamental group depends on which base point the path component is, and in examples you could have different fundamental groups for different path components. So in that case you have a dependence. So this is kind of a simple thing, but not so easy to understand and take care of. Okay, it is a nuisance in a way, but it's still quite easy to understand. But the main case is, suppose x is now path connected. Okay, so now, or more generally, suppose we have x0, x1 belongs to x, and there is a path from x0 to x1. Okay, and let's say gamma from 0, 1 to x is a path from x0 to x1. So let's have a picture here. I have a path here, I have a point, I have this point, I have this point, and I have a path joining these two. Okay, then actually it's quite easy to relate the fundamental groups. So let's define a map. I'll call it tau gamma for transport from pi1 of x1, the final point, to pi1 of x0. And to look at it as a picture, if I have a loop here, for example this one, then I get a loop which is based at x0 by simply following the black path, which was gamma, and this, and then follow it back. Okay, by in other words, tau gamma of the class of alpha is by definition the class of gamma star alpha star gamma bar. Okay, now first of all, this is well defined. Okay, namely, if alpha is homotopic to alpha prime, then gamma star alpha star gamma bar is homotopic to gamma star alpha prime star gamma bar. We saw that homotopic behaves well under products. Okay, there's no problem with it. It's a homomorphism. Okay, this is a little less obvious if you wish, but it is a kind of common as far as group theory is concerned, because let's take alpha 1 and alpha 2 as two curves, and let's look at tau gamma of alpha 1 and star it with tau gamma of alpha 2. Okay, so that by definition is isomorphic, in fact this is not up to homotopy, is equal to gamma star alpha 1 star gamma 1 bar. By the way, I've implicitly used associativity, not bothering to write brackets because the class doesn't depend on that. And here we have gamma star alpha 1 2 star gamma 1 gamma bar. I should correct myself. There is no 1 here, it's just gamma. Okay. But then, so this is equal to the homotopy class of the curve, which is gamma star alpha 1 star gamma bar star gamma star alpha 2 star gamma bar. But you notice that gamma bar star gamma is homotopic to identity, and then identity star alpha 1 is homotopic to alpha 1. Or I could group it the other way. So this is simply the class of gamma star alpha 1 star alpha 2 star gamma bar, and I have just been ignoring parentheses because I can put them anyhow, in particular like this. This is tau gamma of alpha 1 star alpha 2. So this is a homomorphism, and finally we notice that tau gamma bar composed with tau gamma is the identity on whatever the appropriate spaces. Tau gamma came first, so this would be identity of pi 1 of x x1. Well, why is that? Because if I look at tau gamma bar of tau gamma acting on the class of alpha, well, you expand it twice, so it's gamma bar, it's the class of gamma bar star tau gamma of alpha, which is gamma star alpha star gamma bar, and finally I take gamma bar bar, okay, which is gamma itself. If I reverse gamma twice, I get itself, flip gamma itself, and then these two are identity. These are homotopic to the identity. Okay, so this is equal to alpha. Okay, and tau gamma bar composed with tau gamma bar. If I reverse it, it's going to be the identity here, pi 1 of x x0. So what does it tell you? So thus tau pi 1 of x x1 is isomorphic to pi 1 of x x0. Okay, with isomorphism. Tau gamma, if gamma is a path. Okay, well, from x0 to x1. So this is, so we see the dependence on fundamental group. If you have many path components, it depends strongly, but it depends strongly for the rather simple reason that we only see, the fundamental group only sees the path component containing the base point. On the other hand, within that component, or if x is path connected, the group is determined up to isomorphism. However, to find the isomorphism depends on the choice of gamma, so we do not have functoriality. Functoriality is very central to algebraic topology, but we don't have functoriality. Nevertheless, things are not so bad. Okay, we still have a fundamental group associated to a space. If we're just thinking of it as a group, as an isomorphism class of group, we just need to specify if there's a space is path connected, it's a well-defined object.